You all, both from the public and the alumni, for a wonderful talk from Mary Bourke, all about Mars. But first, John Dillon, from the Director of the Alumni at Trinity College, will do a brief introduction. Thank you very much.
Thank you. That was an introduction to an introduction, so I feel a little bit out of place here. I won't keep you long. My name is John Dillon from the Alumni Office. For those of you that aren't alumni, I see a few younger ones, soon to be alumni, I hope. You're all very welcome here to Science Gallery, and obviously alumni coming back to Trinity for this special weekend. You're also very welcome. We look forward to seeing you later on at some of the other talks and tours that are going on. So it's my pleasure to introduce Dr. Mary Bourke, who, if I go through the CV, it's quite an impressive journey around the world, actually, over the years. Dr. Bourke has been a professor here in Trinity since 2012. She's also a lead senior scientist in Planetary Science Institute, and that's based in Tucson, Arizona. She's been in Oxford, the Smithsonian, working in Smithsonian Institute, also in Washington, as well as down in Australia, in particular in University New South Wales. So I'm very much looking forward to this talk, as we all are. I see some people wearing 3D glasses already, which may make it an interesting viewing as well as listening experience. And a new word for me, perhaps for you, but the area of specialism for Dr. Bourke is geomorphologist. Is that right? It's the study of areas of extremes. So with that, I'd like to introduce and welcome and thank you, Dr. Bourke, for your talk.
Thanks. Hello, everyone. Very, very, very warm welcome to Trinity and to the Science Gallery. Today I'm going to take you on a little bit of a journey, first to Mars and then back to Earth. These glasses are called analogue glasses. They enable you to see images that I will display in 3D, but we don't need them yet. So you can leave them on if you like, but things might look a little bit funny, and I'll explain them how to use them in a moment. So what we're going to talk about today is Mars. I don't have a pointer, do I? I don't have a pointer. Okay, so this is an image of our solar system, and we're looking here today at these two planets in particular. And what I want you to note, first of all, is the distance that Mars is from the Sun. The Sun is so important to all of the planetary bodies in our solar system. It's a source of energy. And that energy is not only useful on our planet for driving ecosystems and plants. On other planets, it drives other systems such as wind systems and volatile systems such as ice, water, and other species. It's very similar to Earth in many ways, but because it's a little bit further away from the Sun, its time to get around the Sun is almost twice as long as it is for our planet Earth. And so a year is twice as long on Mars as it is on Earth. However, its rotation, it spins like we do, facing the Sun. Its day and night is dictated by that rotation, is pretty similar to Earth. So the length of a day on Mars is almost the same as the length of a day on Earth. It's 24 hours and 37 extra minutes on Mars. This is a visualization of a topographic map of the planet Mars. It was the first topographic map of a planet in our solar system. In other words, we knew where the highs and lows accurately were on Mars before we knew where they were on Earth. And so what I want you to do is just get a feeling for the topography. The reds and the whites are the highs, the greens and the blues are lows. They are nothing other than topography, the height of the landscape. And you'll see some pretty dramatic features, such as this feature here, the Valles Marineris, and these are volcanoes. They're not snow-topped. They've got actually, that's the height of them. And that's how mountains are built on Mars. One of the ways in which they are by these enormous volcanoes. And this volcano here, Olympus Mons, is the largest volcano in our entire solar system. 22 plus kilometers high. This is the second rendition of topography, but this will go from the north to the south. And what I want you to notice here is that in the South Pole, that little white splotch there, that's ice. That's water ice with some carbon dioxide ice on it. And you see all these potholes all around it? They're impact craters. All across the southern hemisphere of Mars, we have a very heavily bombarded crust that has retained that structure right to present day. But then when we come towards the northern part of Mars and we look at this ice cap on the north, just like we have a polar ice cap made predominantly of water, you'll see it's relatively a lot smoother. So there's a debate currently in the literature about, well, why? Why is the southern hemisphere so pockmarked from impact craters and the northern hemisphere is not? Well, one of the interesting comparisons between Earth and Mars is the impact of impacts, if you'll pardon the duplication there. But here we have a meteor coming in, an image of such impacting through a planetary atmosphere into the surface that results in impact craters. And these impact craters are found across all of the bodies in our solar system. So we've got planets, we've got asteroids, we've got comets, we've got moon satellites. They're all got impact marks on them. So we can see here we've got Mars, we've got the moon, we've got Mercury, and of course Earth, you notice here, because it's actually got vegetation growing inside the crater. This is a crater from Australia. And Venus. This is an image that's taken of Venus using radar technology, which is why it looks a little bit different, because the atmosphere on Venus is so thick that your camera, just using optical wavelengths, won't actually see through that dense, thick atmosphere. On Earth and Mars, when we compare them, they are really quite different in terms of the abundance of these impact craters. Now, I started off by saying that volcanoes was one of the ways in which mountains are built on Mars. Well, impact craters are also another way in which mountains are built on Mars. And if you look here on the right-hand side, the red dots are all the locations of impact craters that survive today on Mars. And on Earth at the moment, the record stands at about 188 craters that we have on Earth. So we all started at the same 4.5 billion years ago in our solar system with our planets forming. It was a very violent phase that was due to lots of bombardment of meteors coming in and smashing into planets, the planets absorbing that mass and growing in that way, that planetary accretion. But now we have Earth with a paltry 188 and Mars with so many more. Anyone want to stick up their hand and say, well, why? Yep. That's true, there are definitely impact craters that have not been found, so that's one of the contributing reasons. But there's some essential difference between Mars and Earth. Yep?
The thickness of the atmosphere?
The thickness of the atmosphere.
Well, it's a lot thicker in Earth, and I guess
Yeah.
that's a lot of like asteroids and very.
But early on, Mars would have had a thick atmosphere, so the same number it would be is likely to be hit by impactors as any other planet.
Is there an asteroid belt close to Mars, closer to Mars?
There's the asteroid belt, but that's not a reason for why it's so more impacted. The reason is that we on Earth have a different atmosphere-surface relationship. We have weather on Earth that leads to the breakdown of different features. They erode by gullies, by rainfall, by freezing and thawing, all the stuff you learned in geography. On Mars, it does have an atmosphere. It does have water in that atmosphere. It's not a very large part of the atmosphere. But what Earth has that Mars does not have is plate tectonics. This idea of plates coming together, and sometimes you're getting subduction of one plate under the other, and essentially recycling whatever was on the surface of the planet, and then coming up again eventually through mid-oceanic ridges, etc. So it's like the crust is cleaned of its morphology periodically by plate tectonics. We don't have active plate tectonics on Mars. And the evidence suggests that there never was. Volcanoes are also incredibly important across our solar system, and here are all the bodies at the moment that we have a history of volcanic activity. Mercury, the Moon, Venus, and again as Mars and of course Earth, but Io has active volcanoes, actively erupting on the surface of Io with loads of lava flows extruding out onto that surface. So, you may not know, but Mars is the only other planet in our solar system that's inhabited solely by robots. Okay, and how do we know this? Well, we have sent a lot, let me just make one last point here about Mars before we go on to robotic invasion of other planets. Mars has seasons just like Earth. We have a planet that has a tilt to it. An obliquity is what it's called. And it's pointing its northern hemisphere in this direction, just like Earth. And it's quite similar to the tilt of, both planets are quite similar, Earth being 23 degrees and Mars being 25 degrees. But the history of that tilt is very different between the two planets. This is a graph that basically shows the variation in that tilt through time. Time is down here in millions of years, so this is the present down here. And so you can see that in the last 2 million years, the obliquity on Mars has varied between 15 degrees and 35 degrees. And we go back in history, and it's been an even higher shift of 45. And some of the modeling suggests that maybe it was even as much as 85. Why? It's got to do with our moon. Mars has 2 satellites, 2 moons, very, very small rocky structures that orbit the Martian planet. We have the moon, our satellite, and the gravitational pull between the two bodies basically keeps Earth pretty stable around that obliquity. But Mars has these 2 much smaller moons, so it's not had that stabilizing effect of staying in its constant obliquity. And that has led to catastrophic climate change in the history of Mars. So you can imagine that you have a North Pole, and suddenly the tilt of the planet changes, and now your North Pole is actually at your equator or close to it, pointing even more, getting more insolation. So the ice caps you had up here now sublimate and maybe even melt, depending on the pressure, the atmospheric pressure, and move somewhere else. So this is a schematic of what we think might have happened in Mars' climatic history, that during periods of high obliquity, you're going to get glaciers forming at the equator on Mars. And during periods of low obliquity, you're going to get that North Pole polar cap extending much further down towards lower latitudes on Mars. So very complicated but very interesting climatic history on Mars. And if that wasn't bad enough, Mars' atmosphere is pretty much depleted. It's very, very thin compared to Earth. Now, the dominant paradigm around that is that basically the core of the planet cooled, and the core of the planet is one of the contributors to a magnetic field, and magnetic fields protect planets from cosmic storms. And so basically, because Mars cooled down, lost its magnetic core, it lost that protective field, and so the cosmic energy has basically eroded away over a couple of billion years, its atmosphere, to being a very, very thin atmosphere today. So here's a beautiful image of the surface of Mars, and you can just see the atmosphere, the limb here. This is Mars atmosphere, very, very thin compared to perhaps, and I'm just drawing this in schematically, the density of an Earth atmosphere. Its composition is very, very different from Earth's. It's predominantly carbon dioxide. You do get wind on Mars, but it doesn't have as much energy behind it. You would need hurricane force winds that we have here on Earth in order to pop up a grain of sand on Mars. So, exploration. It's been a really tough story. We have lost nearly as much, or more I should say, missions that have gone to the planet Mars than we have successfully orbited or landed on that planet. So I joined NASA back here when the idea was follow the water. We want our scientists to basically look at the data we're sending back from Mars, to look at signatures of was there ever water on Mars? If there was, where was it? What form was it in? Then we moved into, because we had confirmed, yep, there was water on Mars, we wanted to talk about habitability. Is there a habitat for life on Mars in these past or contemporary watery environments? And now we're in a phase, which is our future missions, the next ensemble of rovers and orbiters to go to the planet to actually search for signs of life. So this is the payload that's at Mars right now. It's a combination of satellites and rovers. So we have a very international contingent there with missions from India, Europe, and from the United States of America. And they're collecting Very, very important data, and each mission that goes up collects better and better data, higher resolution. We can see in more detail the surface features. We can penetrate through the crust down several miles. We have these two robotic field geologists, the Mars Science Laboratory here, which was landed in 2012, is just a payload of amazing. It's basically like a science lab on Mars. It has the ability to blast rocks with lasers. It can analyze samples. It can take images. It can build, the data can be used to build topographic models. We also sent two rovers, Opportunity and Spirit, much earlier on in 2004. And all of these rovers and landers are basically initially set to run just for 90 days. That's what the funding is in place for. That's what the engineering is in place for. Anything longer than that is pretty miraculous. Well, we have this ensemble here. This is when I started working on Mars. We had this little suitcase-sized Sojourner rover that basically could trundle over very slowly to a rock and look at it, take a picture, and come back. Okay? Since then, we sent twin sisters up, Spirit and Opportunity, and now, as I say, we've got this fantastic robotic suite of instruments on the planet. But the people who run Opportunities, the Spirit died quite a while ago, and Opportunity might be dead. They're actually waiting now to get a signal back from Opportunity. And you may ask why. Well, Mars, just very recently, is just coming out of a global dust storm. We have dust storms on Earth that build up from places like the Sahara Desert, and they blow sand across the surface and up a little bit, maybe a meter and a half, but the dust goes up into the atmosphere. We have oceans that basically stop, and mountains, huge mountain ranges that would stop certain amounts of that dust penetrating to become global. We don't have any record of any global dust storm on Earth. But on Mars, it doesn't have these oceans. So these huge events can become global in nature. And this is an image of Mars taken in the last known global dust storm, which was in 2001, where you can see the surface of Mars on the left, pre and during the storm, the dust storm there in September 2001. So we're hopeful that Opportunity will continue to collect data and communicate back with Earth. The issue is, and the relationship between the dust storm is that they're powered by solar panels. And those solar panels are facing up to the sky. And pretty much there's a constant rain of dust out of the atmosphere. But when you have a dust storm, it's accelerated. So if your solar panels are covered in dust, you can't recharge your batteries, so you can't phone home. So we've had that happen before, and very opportunistically, a sort of a tornado passed over one of our rovers and sucked up all that dust and cleaned the dust panels for us. But I don't know if that's going to happen again. We can live in hope. So with all of those robotic missions that have been sending home data quite recently from Mars, we have learned an awful lot about the planet and how dynamic it is. It was a remarkable surprise to the scientists just to see how dynamic the surface of the planet is. So I'm going to show you some images that reflect that dynamic behavior. So what you're looking at here is a top-down image of an ice cliff at the North Polar Cap on Mars. And this feature here is an avalanche that was caught in action by one of the images that were taken from one of these high-resolution cameras above the surface. So this is a dusty and water ice-rich avalanche. We now know, this is an image that was taken of a site. We have a before and after. Because these satellites have been there so long, they're able to return back to the same location and take a snap of surfaces after a period of time has occurred. And so between July in 2010 and May 2012, this happened. And this is an impact crater. It's a small impact crater, but you can see how wonderfully it basically leaves a mark, so we can start to understand how frequently these happen. But also it excavates sediment from beneath the surface. It's very difficult for us. We can see the surface in good resolution, but in terms of subsurface, it's very difficult for us to understand what's in the subsurface. Sometimes these new impact craters throw up amazing data. And so what you're looking at here is a crater that impacted into an ice-rich regolith, a soil, and threw up ice. How do we know it was ice? We were able to point a camera, an imager that could look at a different part of the spectrum to detect an ice signature, and it disappeared. It basically sublimated with time. We kept going back and back to it, confirming for us that models that we had generated of water on Mars, having water beneath the surface, were correct. But of course, impact craters tell us, because they expose in their walls bedrock, which we're not able to see from orbit. We're able to go to the walls of these craters with our rovers and image these sediments. And what we're looking at here is, very interestingly, down here, these are all sediments that were laid down by sand dunes on Mars. And above it, you've got all of this highly fractured material, and that's all cracking of the surface due to impact itself. And this dark stuff here is all basaltic sand, which is found across great swaths of the planet Mars. Again, this ability to keep returning to the same spot allowed us to detect new features that were surprising and exciting. So what you're looking at here is a sequence of images through time. And you'll notice these streaks moving down. These occur called recurring slope lineae, and they are hypothesized to be put there by seeping water on the surface of Mars, active today. Now, we don't have the atmospheric pressure and the temperature to allow fresh water to exist on the surface of Mars. The pressure is too low and the temperature is too low. So basically, if there was water, it would just basically bubble and disappear. So in order for these to exist, these slope lineae, and in order for them to be water, they would have to be salty water. They would have to contain quite a large proportion of salt, and that depresses the freezing temperature and allows it to exist in its liquid state. Now, we're not saying that you've got water running down the sides of craters on Mars. It's more like a seepage, a very slow darkening of the soil, because you've got this kind of pore water moving through the very tip-top layers in this location. All we can do is put forward hypotheses. We see the information, we analyze the data, we do what we can to collect the relevant information, but all we can do is put forward hypotheses, and these hypotheses, they need to be tested. In fact, one of the team that proposed this idea was a team from the University of Arizona, and one of their own, a graduate student, said, I don't think so. Hang on a second, I don't think these are anything to do with water. I think these are just dust avalanches. Avalanches just running down a slope due to disturbance by wind. So the jury's out. But this would be one of the most amazing places to go to look for signs of life, because where you have liquid phase water, you have the potential to form life. But then if we go there, we're bringing our own microbes and we're destroying the environment. So it's problematic, I think, is the best way to put it. In terms of this theme of liquid water, here we have the Phoenix lander, now dead, unfortunately, killed by seasonal CO2 ice, carbon dioxide ice that basically smashed its solar panels. And it landed down, and you can see these jets underneath, and it blew up this huge dust plume from underneath it as it landed. And then it took out its camera and looked underneath, and this is what it saw. Here, a white something, they thought. Rock? White rock? And then they did analysis on it, and that is pure water ice. Pure water ice under that much of sediment close to the North Pole, about the latitude of Norway, about 67 or so degrees north. And also, they kept pointing their camera underneath here to check if it was going to disappear or sublimate or something. And then they started to notice, and I apologize, I don't have a very good image of this to show you, water droplets, so what they hypothesized to be water droplets forming on the legs of the Phoenix lander. Again, we have this issue of it's too cold and the pressure's too low to have water. And so it was put forward the idea of salty water. And the actual salt is perchlorate, of which we have evidence for, with other instruments, of being abundant in the soils on Mars. Really bad for humans. It gives you thyroid problems and other medical issues, so not great. Dust devils. So these are one of these like mini tornadoes I told you that came across one of the instruments and sucked the dust from the solar panels and cleaned it so it could keep going. These are phenomenal. These are activated during the warmer seasons. It's not like summers here, equatorial summers on Earth, but we have recorded higher temperatures in the order of 35 degrees centigrade, but normally the average global temperature would be around minus 55, much, much colder at the poles. This is a sequence image of a Barcan sand dune. Again, the dark color is the mafic sand, the basaltic sand. And prior to these images being taken, we thought the sand dunes were basically fossil sand dunes belonging to a previous climate when the wind was howling across the surface of Mars. But lo and behold, we found evidence for these dunes actually creeping, and they're creeping forward at about 1 meter to 2 meters a year. And this was very, very difficult for people to understand, because remember, the atmosphere is so thin that it takes so much energy just to lift up a grain of sand. But one of the advantages of having a thin atmosphere is that the minute that sand grain is lifted up, your thin atmosphere is not providing the same amount of resistance to it moving through the air as it would on Earth, the frictional resistance. So a combination of different efforts, including very high speed winds, is allowing the dunes on Mars to migrate forward. And it's a very, very important process, probably one of the most important processes on the surface today, this wind, where it's not only moving and depositing sand, it's eroding bedrock with these yardangs that have been formed here. This is what we would call a yardang, and this is a dune that's adjacent to it with sand actively blasting and eroding this bedrock. So now let's have a look and see what it's like on Mars. So these are images. The first images are taken using Rover. Whoops. So I just need a power cable if I could. Could I just have a power cable? It's in my briefcase. Thanks a million. So the right way to have these on is have your the blue over the right eye. If you have it the other way around, you won't get the same kind of effect. So put the blue, so you just turn it the other way around if you've mistakenly. So can everybody see this in 3D? Tell me what you see. What can you see? This is an image taken from the rover as it was climbing up a hill side of an ejecta blanket. Thank you. So the rocks look pretty sharp and spiky, don't they? So this is very typical of deserts here on Earth, where we find abraded rocks that have been sandblasted. So if we move on to the next, so this will just be a collection of various images. You can leave your glasses on as we go through. So this is a view as if you were standing on the surface of Mars, looking over the edge of an impact crater across into the interior of that impact crater. This rock here, you can see, again, has evidence of being sandblasted, these grooves eroded out by sand. So it's wonderful because this particular robot explorer is about the size of a 6-foot person here on Earth. This is false color. This is not the color of the surface of Mars. But it's an inverted river channel. It's a meander bend of a river. And you can see here these arcuate features here. And this is where the river used to be. And it migrated laterally, just like the rivers do here on Earth, with time, reinforcing an idea that we had a very robust hydrological cycle on the planet Mars, where rivers were flowing perennially all the time. We also have evidence of ancient flood channels. Again, here is an anaglyph image where you can see the channel here that the water would have flown through. And interestingly, what I want you to note is there's a big channel here, there's a big hole here, and there's little channels coming out here. And we published a paper on this particular site suggesting that this is a collapsed cavern, just like you have over in the Burn area in Ireland, where you have this karst region where you've got all of these in the limestone collapsed dolines and structures in the Isle Louis caves underneath. We think there's a system like that on Mars, because this river clearly has had its water captured and flow down this particular cavity system underneath, because it's different on this side from this side, which suggests a different activation through time. So another location for potentially looking for life, habitats on Mars is underneath the surface, where the life forms would be sequestered away from the radiation, the destructive radiation that the surface receives. Again, another flood channel. These are enormous, and you can see here also an impact crater, an older impact crater here, and these are features formed by lava. So we talked before about the erosion of the surface by sand. So these are some of the landscapes that are created because of that. So these are sand dunes that are advancing in this direction. These are horizontally, sub-horizontally bedded bedrock that's been sandblasted by these dunes and other sand from other sources. And these dunes on Mars are very, very different from the dunes on Earth. They are enormous in size. So these are about 50 meters in height, and the average of Barchan dunes on Earth is 5 meters. So these are towering edifices of black loose sand that are moving across at a rate of 1 or 2 meters per year across the surface of Mars. And this is where some of them come from. This is part of the polar ice cap here. This is a vertical cliff, and you can see these layers of sediment here. And the dark layers are feeding sand out into this area here, which is a dune field at the north pole of Mars, an active dune field. And again, we can see this beautifully wind-sculpted landscape of deep cavernous valleys, often in other locations, but here just canyons and residual peaks. This is a channel that we actually think has been eroded by wind in Gale Crater, which Curiosity rover is right now. So wind can also, as an active force, can erode canyons on the planet Mars. This is an example of a simple impact crater, where you can see it's pretty much bowl-shaped. This is the ejecta issuing out from it once the impact happened, and these are scattered all across the surface. We also have, I mentioned impact craters and I mentioned volcanoes, but we also have tectonics, not plate tectonics, but tectonics that have been formed by the building of volcanoes on the crust. The sheer weight of that mass has caused fractures and cracks to emanate out of it. And so what you're looking at here are fault-controlled cliff lines, so a fault developing here, and then further subsidence in sequence away from it with these huge caverns that have basically just collapsed down into an accommodation space beneath. And again, this is a kind of an indication of just how old some of the surface of Mars is. It's so old that not all of the canyon imprints are these holes in the ground, but you have these canyons that were once filled with sand and gravel that became cemented. Then the wind eroded the landscape, and they're left standing above the landscape on Mars. And again, in terms of the power of the wind, here we have an impact crater. This is a real feature. This is not made up, although, you know, hello. So this is coincidentally an impact crater with three younger impact craters, lots of impact craters on the surface, creating this feature. And finally, these are cone-shaped structures that are not volcanic in terms of lava, but are volcanic in terms of mud. They're hypothesized to be formed by mud oozing from the subsurface up through and extruding, just like a lava magma volcano would operate, but the sediment is not basaltic lava. It is the solidification of mud and sand that has been extruded from pressure on the surface. All right, so that's it for the 3D images. So I want to talk to you a little bit about planetary science and what it is that we do. So it's a scientific study of planets and planetary processes, and it's basically all planets and all planetary bodies. So it's not just the Earth and Venus, it's also asteroids and comets. And so this is a 3D kind of visualization of just how important and how various all of these planets are across our surface. So here you've got an axis that talks about tectonic processes. And here you've got an axis that talks about atmospheric and fluvial processes. And here you've got one that talks about volcanic processes. So this graphic is basically showing you the importance that these different processes have had on different planets. So for Earth, for example, okay, volcanic processes quite important. Atmospheric, aeolian, fluvial, so the wind and water, very, very important. And tectonic processes, very important. And then we look at Mars. It's kind of midway, and it's midway because halfway through its history, the atmosphere was depleted, so that became a less powerful mechanism for erosion on Mars. But we do have volcanic processes as being quite important. So there's similarities between Mars and Earth. Now, as was explained earlier on, I'm a geomorphologist. What does it mean? It comes from a Greek term meaning earth, form, and study. We study the landforms and the processes, both chemical and physical, that operate near the surface. So when you were in school and you learned all about oxbow lakes and river meanders and beaches, that's what we study. But geomorphology is a bit of a mouthful. Geomorphology. So I describe it as the science of scenery. That's what we do. We see landscapes and we figure out how they change through space, like why is that one different from that one, and through time. What's the evidence that it's changed through time? Because in those signatures, we can find imprints of past climates as well. If there was glaciers, and they're not there now, we know it was colder and there was more moisture around. We're a bit of an odd bunch. We can be found in deserts, walking around, just looking at the ground. And sometimes we get very, very close to the ground. We're not sniffing, we're taking measurements here. I am in Namibia measuring the slope of a ripple, and here is Grace in Antarctica trying to install a seismic sensor in some very, very important work that we'll talk about in a moment. So this is how we go about collecting data on a planet that is so far away from us. We use remote sensing, we use images that come back from satellites. We use analog studies and we use lab studies to replicate similar atmospheres, similar atmospheric pressures. But today I'm just going to focus on this analog because today we're talking about Earth. And so our science is one where we collect a lot of quantitative information to build topographic models to compare them to landforms that we find on other planetary bodies. So here we are testing an idea that maybe some of those cones that I showed you that I said were mud volcanoes, well, maybe they're mound springs. So mound springs are also these conical shaped features, but they're not formed from oozing mud. They're formed from water coming up, evaporating and precipitating salts as it evaporates, and they build up this cone structure. And we have a beautiful suite of them in Australia. We end up digging an awful lot of holes. I mean, basically for a period of my career, when people asked me what I did, I said I dig holes. In fact, the technicians in the university in Australia did a grave diggers course because we dug for safety, obviously. You know, you had to ballast up the walls of any deep excavation pit that we were then invited to climb down into. Deserts are a very good analog environment for Mars because it is a very dry planet, but it's very, very cold. So some of you might visualize deserts, okay, we're thinking the Sahara, we're thinking huge sand dunes, but there's a whole range of desert types. And importantly, they're hot and they're cold. And I think the cold deserts are quite a good analog for those on Mars. So this is just a simple map of all of the deserts of the world. The ones with the yellow dots are the ones that I've published on and done work in, and the ones with the brown dots are the ones that I've visited and observed different processes on. So I have been pretty much around the world looking at deserts, which is why NASA was interested in employing somebody with my skill base to work and look at images of Mars. But cold deserts seem to be quite the key. Now here's a picture of the Sonoran Desert. I not only worked in them, but I lived in them for a little period of time. I wouldn't advise it. It's very, very hot, despite what this slide says. So these are the saguaro cacti that you see in all the Western movies, in a very unique event where snow actually fell because of the altitude that they were at. But it's all about water and the search for water on the planet Mars, and that's guided a lot of my research. So when we go back in time, there are lots of evidence to suggest that water once flowed freely on the surface. There are people who think, remember that very smooth basin that I talked about at the northern plains of Mars, and this is the Olympus Mons, the highest volcano, that used to contain a very large ocean. We have these beautiful deltaic deposits that are indications of rivers flowing into craters that contained lakes. Some people even think that there's evidence for strand lines around the edge of this. It's contentious, but the evidence is building strongly. And so when we map these out, we can basically map out the history of that river flow. And estimates that we did on this particular deposit allowed us, using an analogue in Australia that flows into Lake Eyre, that we proposed that this particular deposit here had sustained flow for 150,000 years on the surface of Mars. So that you had free-flowing water pretty much consistently, a fantastic potential environment for looking for life. And you may have heard recently of other discoveries on Mars. And I have to say, there's always this announcement of water has been discovered on Mars, and we go, again? Because we've known that with the ice caps and in the subsurface, there's been water for quite some time. But this was quite exciting, and this happened just very, very recently, and very proudly it was a European mission that made the discovery. And so they looked down at the South Pole, and they have this radar instrument that can penetrate down beneath the surface and look for reflection. So it's what's called an active sensor. It's sending its energy down and waiting for it to come back, and it comes back in a changed form, and it can interpret what that means. And so what they did was they made this discovery, and they were unsure about it because the next time the satellite went over the exact same spot, the data didn't show it. So they went back again and again. They went back 29 times. And they ended up being pretty confident that that spot there was reflecting water, but it wasn't ice water, it was liquid water. So probably the pressure from the crust itself and the salt that we talked about before had led to the presence of this body of water in the subsurface on Mars. So we're looking at a very deep body of water, about 1.5 kilometers deep. They say it's at least a meter. That's because as the radar reflector goes in, it can penetrate into anything that has a strong reflector, about a meter, and then it comes back. It could be 10 meters deep, but that's the penetration ability. So this was absolutely tantalizing. So this is the radar signature here. This is the icy cover. This is probably bedrock. And that blue there is where they think this lake is positioned. So now they're going back. They're going back all around the South Pole to look for other locations. And really what they want to find is that they'll move this instrument closer to the equator, because we can land more safely in the equator and our equipment lasts longer in that equatorial region. In the poles, we can send missions there. They're far more treacherous to be successful in their landing, and they don't tend to last because they die during the Martian winters. But we do have a beautiful analogue that was worked on and discovered prior to the Martian discovery. So this is Antarctica. And so what we have here is a lake in Antarctica, which was discovered beneath 800 meters of ice. And they drilled through it, and they put a camera down, and the camera bottomed out, and they could see images all the way down of where the drill had scalloped out the ice, and they were waiting and waiting and waiting and waiting, and then it went dark, and they went, oh God, it's, what's happened? And then it started to clear, and it looked like this murky, muddy water. They thought from the radar data that they were looking at a lake of 25 feet. It was Americans from the University of Illinois, 25 feet deep. And when they got down there, they realized it was actually water for 5 feet and mud for 20. And they sent down a core, and the core pulled back up, and they took some of the sediment from that core and looked under a microscope, and they found skeletal remains of diatoms. Something like this. This is not an image of what they found, but this is evidence of life that existed probably 1 million years ago. At least, 150,000 years ago, before the ice came over and covered up this lake, when it was a surface water lake. And so there's two things about this. One is they've developed technology to drill through significant thicknesses of ice. It's an incredibly difficult job. And secondly, they have found traces of life beneath that ice. And so this gives us great hope and a direction in terms of looking for life on Mars. But we've been here before. We have had an instrument called the gamma ray spectrometer that was able to show us that there was water across the entire planet beneath the surface. So this diagram down here shows you what that data said. So where it's pink, it's high water content, and where it's red, it's low water content. And so it looks like at the North Pole, and as you go towards the equator, the ice gets lower in the subsurface, but it's there. And sources of this ice can be in the geological history of Mars, but also we do have water clouds moving across the atmosphere on Mars. And we had a laser in that Phoenix lander that pointed up to the clouds and scanned them with the laser and was able to detect what were called fall streaks, which were these streaks of volatiles that were identified as H2O falling from the sky as winter approached. Now, they weren't seen to hit the ground, but it was early on in the winter and they were predicted to hit the ground. And then modeling has basically shown that you're getting these tremendous snowfalls, water ice snowfalls, thunderstorms on the surface of Mars periodically. Now, the dominant ice is carbon dioxide ice, and it falls as snow. It forms slab ice on the ground. It diffuses into the shallow subsurface. But I'm kind of interested in the water ice because if we can find locations where there are deposits of this water that are kept safe in the subsurface that astronauts could have access to, they have a source of potable water if they ever go there. So seasonally on Mars, you get a covering of snow and ice condensing onto the sand dunes. And in looking at some of the very detailed images of sand dunes in the North Pole of Mars, like we have here, these are basaltic Barcan sand dunes, we noted these features here, these indurated ridges that were sticking up out of the dunes. We also noticed these pockmarks, these holes in the dunes. Now, if we go to another wonderful analogue, down again in Antarctica, we can see that in the dry valleys in Antarctica, in Victoria Valley in particular, you have beds of strata that are exposed. These are paleo sand dunes that basically have moved away from that location, but their sediment has been frozen into the permafrost. This is a picture of the dry valley in Antarctica, and here you have a layer of snow and ice that's preserved inside the sand dunes there, and you can see them sticking out. And here's another one sticking out of a sand dune in Antarctica. So now we're seeing that we have an analogue in Antarctica that is perhaps opening a window of forming a hypothesis for what these ridges on these dunes on Mars might be. And here you have these sinkholes, which is formed in Antarctica again from the sublimation of the ice that's trapped underneath. It basically sublimates away and the sand sinks down into the hole. And so it is potential that on Mars we might have something like this. These are called Niveo-aeolian deposits. They're deposits of snow and ice that are interbedded in our polar dune fields here on Earth, but towards the northern hemisphere and the southern hemisphere. And if this is the case on Mars, you have layers of pure water ice that are preserved, and they're protected because the wind blows sand and protects it from sublimating, and maybe there's another snowfall or another blast of wind and ice deposits on top of it. Some of it's quite dirty, but some of it's quite clean. Okay, so I'm going to actually leave it there because we started late and it's 5 minutes before the end. So thank you very much for your attention.
So if anyone has any questions, we have a little time for some audience Q&A. We've got microphones on both sides.
Is there any likelihood that our planet Earth will end up like Mars?
Yes, in a very long time. That there is a body of scientists that suggests that might indeed happen. If our core cools, which it will do, they're all cooling down. So we would need that to happen. I think the necessity for us to think about the habitability of our planet comes more immediate in terms of the destruction and the process that we're doing. But geologically, yes, eventually it will, yeah.
Is there molten lava under the crust?
No. Well, maybe. So time on Mars is a little bit different. So we think recent here is like 1,000 years. On Mars, it's maybe millions of years. So there is some evidence that there's been recent volcanic activity extruded through basically the fissure flows, so cracks, not volcanoes, where lava has come out. And they think that they're less than 10 million years old, which is really young in geological history. It can't be explained by what we know of the crust. The dominant idea is that no, there's no lava active underneath. Yep.
What were the skeletons that were found in the lake like?
They were microscopic, so you wouldn't see them if you picked them up in your hand. They were ancient, they're called diatoms. So they're little critters that live in water, in lakes in Ireland and all over the world, that are found, that live right in the water interface. And when they die, they float down to the bottom and they're laid down on the muddy sediment that's at the bottom of the lake too and buried. And so that's what they pulled out of Antarctica. And that wasn't Mars, that was Antarctica. And so there's a potential, if we were to look, that some primitive life form might be found.
Do we know anything about the grains, the texture of the grains of the sand on Mars?
Yes. So
is it very smooth? Is it very sharp?
It's both. So some of the instruments have gone right up and photographed quite recently in Gale Crater, a dune called Bagnall Dune, imaged the actual sand grains, and some of them are absolutely smooth as a sphere, and some of them are quite angular and mixed in. So we know that indicates to us that grain has been transported over either a long period of time or a great distance. To become that smooth, because the smoothing happens by them smashing off each other during transportation. So we have both angular and smooth, and the grain sizes are quite similar to those that are found in the sand dunes on Earth. Yep.
Do you know the chemical composition of the rock and the sand grains?
Yes. So it's mainly mafic, it's mainly a basaltic source, but there's different generations of those mafic grains. So some are olivine, which indicates a very low water-rich weathering environment, very dry. So because olivine it weathers really quickly when it comes in contact with water. And other is actually clays, phyllosilicates, which is indicative of a very wet weathered environment. But there's carbonates on Mars, there's lots of sulfur salts, gypsum, but dominantly the lithology is mafic, it's basaltic.
So you talked about looking at modern analogues. Have you looked at the Permo-Triassic, for instance, and the dune fields when you're looking at Mars?
Yeah, I haven't, but people have. And one of the interesting things is that one of the features they found were evidence of slumping avalanche phases on these that wasn't due to dry grain flow but due to kind of wet sand. And work I did in Namibia on a different project basically showed that slumping doesn't have to be rainfall, because they hypothesized it was torrential rainfall during that period of time and inferred a monsoon from it. And the work I did in Namibia basically showed that no, it's just fog that drifts in from the coast can saturate and make it so heavy that it also slumps. So it's wonderful. I mean, I think a take-home point should be that not only are we investing heavily in understanding the rest of our planetary system, but we're learning so much about Earth as a result, because we as scientists are being deployed out to all these different locations to investigate these potential landforms, to investigate these potential habitats. And we're learning more about our own planet through that process that we then apply to Mars, but we also apply to Earth.
So when you were referring to earlier about how like a single grain is very hard to be lifted off the surface, why is that?
Because the atmosphere is so thin. So the actual pressure that's required to build up to give the momentum to that lift force is much, much higher. So you need a much higher wind speed because the atmosphere is so thin. But once it gets lifted up, then it flies. It's kind of much, much longer path before it drops down again.
Just on behalf of everyone here, I'd like to give a very warm welcome and thank you to Dr. Mary Bourke for a wonderful lecture today. I'm delighted that based on the lecture, I think there's a lot of geomorphologists that on the beaches during the summer months that will probably be joining your ranks in years to come.
Yeah.
So on behalf of everyone, thank you very much.
Thank you. Keep these, and there's images online called anaglyphs, which you can use them to look at other images in 3D, or you can just pop them up at the top and we'll use them again. Reuse, reduce, recycle, repair. Thank you.